Good afternoon. My name is Ifan Stephens. I'm a reader in the Department of Materials at Imperial College London. So you're very welcome to this panel discussion on sustainable fuels as part of the Future Energy Festival, hosted by Energy Futures Labs, which is the Energy Futures Labs is Imperial's Global Energy Institute. So I'm also joined by Jason Hallett, who's Professor in Sustainable Chemical Technology in the Department of Chemical Engineering. Also Anna Henkin, who's a lecturer also at the Department of Chemical Engineering, and Dr. Reshma Asif, who's a research associate joined between Department of Chemistry and Department of Materials. So, well, each of us are going to introduce ourselves first, and then there'll be time for you to ask questions. So we want the discussion to be as interactive as possible, so please get involved by putting your questions in the quick Q&A box on the right hand of the screen. So I should also mention this session is being recorded and will be made available on the Energy Futures Lab YouTube channel in due course. If you'd like your name not to be on the recording, you can submit your questions anonymously. If you'd like to actually to give your name, that's also fine as well. So the event will not last any longer than 1 hour. So just to introduce, give a general context. So as we know, the COP26, in COP26 governments around the world, they agreed to phase out coal and to decrease emissions by 50% globally and over 50% in developed countries. So this puts enormous impetus on us as a society to find alternatives that are sustainable in the long term. Also means there's a huge amount of capital available for looking for alternative and more sustainable energy solutions. So we're at the stage where the average cost of energy from wind and solar power is often cheaper than fossil fuel alternatives. Especially solar power has dropped in cost by an enormous amount over the past few decades. However, we still need energy when it's not sunny or windy. So one way of storing energy is, of course, through batteries and enabling the electrification of transports. And this was the topic of the prior discussion we had in the festival this morning. However, batteries do not store enormous amounts of energy. Fuels store much more energy. So one thing to bear in mind, so 1 kilogram of petrol is equivalent to 58 kilograms of lithium-ion batteries. However, 1 kilogram of hydrogen is equivalent to 150 kilograms of lithium-ion batteries. So the implication of this is that it would be much better if you could use a fuel like hydrogen or another alternative for applications where we currently can't use batteries and where we'd rather not use fossil fuels, or we can't use fossil fuels in the future. So these include things like heavy transport, like trucks and shipping, and of course for aviation fuels, where you really need the medium of storing energy to be as light as possible. You simply won't be able to go on a transatlantic flight using lithium-ion batteries. It's impossible. So also, apart from powering our transport, fuels are also important for other applications. In particular, in the UK, there's a lot of interest in using hydrogen for heating buildings instead of natural gas, which we currently use. Of course, when you burn hydrogen, it just makes water. Also, that we need to decarbonize industry as well. So right now, for example, coal is used for making steel and makes enormous amounts of CO2. We'd like to make fuels that can fuel industry without making CO2 emissions. So the way I say it, there's 2 ways we can make sustainable fuels. Either using bio-derived fuels, which Jason will talk about in a few minutes, or electrofuels. So an example of electrofuel is hydrogen, and more specifically green hydrogen. You can make that by splitting water using electrolysis, which Reshma Asif will talk about in a minute. Or otherwise, you could also split it using photoelectrochemistry, which Anna will talk about in a few minutes. Another example of electrofuel would be if you took a surplus CO2 from a point source, for example, or if it's captured from air, and then you reduced it into a liquid fuel like ethanol or methanol. Because the liquids are very, very easy to transport and they're more easy to integrate with current infrastructure. Another example of a sustainable fuel is ammonia. So ammonia right now is a chemical that's produced in larger quantities in the world, but it's mainly used as a fertilizer. However, there's a lot of interest in using it as a high energy density fuel. It's also the key point is it doesn't make any CO2 when it burns. So if you can make the ammonia from renewable fuels instead of from natural gas as it's currently made via steam formation, it would be a lot better. So my own personal research is on catalyst materials for electrochemical devices, such as, for example, if you want to make green hydrogen from water splitting, or also for other processes, for example, for making, if you want to convert CO2 into fuels or to make ammonia. So many people are familiar with catalysts. I guess most people, the first thing they think about is catalytic converters in cars, which minimize harmful emissions from combustion engines when you combust fossil fuels. However, it turns out that catalysts also control the production and the utilization of sustainable fuels. So what I think is really, really fascinating about catalysis is that it marries fundamental science at an atomistic level to real life applications and everything in between. So it's a really exciting area of research. So I think that's enough introduction to myself. And now I'd like to pass the floor over to Jason Hallett, who will also give you an introduction to himself and his research.
Thank you, Ivan. That was a fantastic overview. So I'm Jason Hallett. I'm a professor in chemical engineering, as I've mentioned, and I work in bioenergy production, especially sort of processing and production methods for different fuels, chemicals, materials, whatever. So we're looking in the area of liquid fuels, basically the production of bioethanol from trees. The reason that we're interested, or the reason I'm interested in this research topic, is that bioenergy is the only large-scale energy production vector that it actually has the potential to be carbon negative. CO2 emissions are inevitable, so human activity, there are areas where we cannot have a completely carbon neutral activity. We're not carbon neutral. We emit carbon dioxide all the time, especially when I'm talking. And so bioenergy has that one inbuilt advantage that it can actually remove more carbon from the atmosphere than it emits when you utilize it. This actually cascades through all of the applications, which is quite exciting. It's an enabling technology, so it can be used to produce electricity, which of course is done right now, actually at very large scale in the United Kingdom. And it can also be used to produce hydrogen. So as I've mentioned, if we're scaling up our hydrogen production in the future, we're going to need hydrogen from a lot of different sources in order to decarbonize the grid and decarbonize the chemical industry and decarbonize the fuels industry. We would require 10 times more electricity than we currently produce. And since about 1/6 of our energy is renewable, that means we would need 60 times the renewable energy that we currently produce. And biomass is an outstanding source of hydrogen because it comes without the requirement to produce electricity in the intermediate. So you can sort of use it at large scale and electricity at smaller scale. As I mentioned, I work on bioethanol, or I work on actually on renewable energy in general from wood and from also waste material in the circular economy. The reason I like the liquid fuels angle is because somewhere between 98 and 99% of the current vehicle fleet requires a liquid fuel, which is basically petrol in the United Kingdom, between 10 and 15% ethanol in countries like the United States and China. In order to turn that vehicle fleet over to whatever, electricity or fuel cells or whatever, is going to take about 30 years. And in the meantime, we're going to need a liquid fuel. So we can either continue burning petrol for 30 years, we can continue steam reforming methane, produce hydrogen for 30 years, or we can use biomass as an intermediate that would be, as I said, potentially carbon neutral on all three fronts. So that is my introduction to why bioenergy is so freaking awesome and makes everything else more awesome around it, including electricity and hydrogen.
Sorry, I had a problem unmuting myself. So thank you, Jason. That was really fascinating. introduction. So I'd like, before we move on to Anna Henkin, who's going to talk, I'd like to remind the audience, please do post your questions on there's a Q&A box on your screen. Please do post some questions. We're really eager to answer your questions once we finish the introduction. But if you can post your questions right now, it would be really, really good. It should be on the right-hand side of your window. Okay, thank you. Anna, please go ahead.
Hello, everyone. So I'm Anna Henkin. I'm a lecturer in the Department of Chemical Engineering. And my relatively recently established research group is called the Electrochemical Systems Laboratory. And what we do is we develop electrochemical solutions to various types of industrial problems. So these can include material recovery from wastewater streams, from batteries. We also look at corrosion. And what we typically do is we start off by researching individual reactions that are of particular interest to us. So for example, either metal reduction or hydrogen evolution, and we measure them on a small scale. We predict the thermodynamics, we measure the kinetics, and we get a really good understanding of how to control the reaction that we're interested in and how to maximize the yield. And the next step is to then start to scale up the complete process. And for that, we do microkinetic and multiphysics modeling to help us design electrochemical reactors that we then commission, build, and test in our laboratory. And from that, we learn a lot of things. We learn how well we understand the process, how well we control it, and whether it actually makes sense from an energy input point of view. And finally, this enables us to propose a design for a prototype that could then potentially be of interest to industry. So one of my primary interests that is particularly pertinent to this discussion today is the production of hydrogen from water electrolysis that's powered by solar energy only. So we call this solar hydrogen, meaning that the only energy used to produce it comes from the sun. So this is something that could be done today already by coupling arrays of photovoltaic panels to water electrolyzers. So these are two completely separate systems that have been developed separately from one another, and all you're doing is combining them together. So to make the operation optimal, you normally have to use power electronics, which add the energy penalty to the whole process. They add to the cost. And in addition to that, electrolyzers are frequently quoted as being quite expensive, so associated with a high capital cost, because, for example, PEM electrolyzers use platinum group metals, and we all like to say that that's not not a great thing, and we need something cheaper and more sustainable. So it's not surprising that people have had the bright idea of, well, let's take these two separate systems and combine them into one device, so that instead of two separate processes, you combine everything in one unit, lowering the capital cost. But basically, all of the constraints that up to that point have been placed on two separate systems are now placed all on this one system. So the number of problems that have to be solved to get it to work, the list is very long. So the materials, which in PVs are encapsulated, which absorb light and convert it to electricity, are in the two combined system. They're actually immersed in the electrolyte. So material has to be a good absorber. It has to be stable in, for example, an aqueous environment. And it has to be a great catalyst as well. So the bottleneck at the moment is in materials, but my focus is on taking examples of materials that perform okay and designing what's called photoelectrochemical reactors to accommodate them. And we do this experimentally and using modeling to try and avoid the various losses that will occur in these systems. And I'll be happy to answer more detailed questions about that. Thank you.
Thank you, Anna. I'd like to pass over the floor now to Reshma. So do remember to post some of the questions as well. We've already got some. Looking forward to more.
So thanks, Ifan, for the introduction, and I'm happy to be here. My name is Reshma. As Ifan mentioned, I'm a research associate jointly in the Department of Chemistry and the Department of Materials. And my research involves using low temperature water electrolysis to produce green hydrogen. So like Anna, Jason and Ifan have already mentioned, green hydrogen is a really exciting energy vector because it really enables us to decarbonize very challenging areas of society like heavy duty transport, a lot of chemical industries, as well as provide some of those domestic heating needs. So specifically in the UK, currently we produce about 27 terawatt hours of hydrogen per year, and about 96% of this is produced using steam methane reforming, which produces carbon emissions. Looking at 2050, we are forecasted to produce about somewhere between 500 and 700 terawatt hours of hydrogen, and we want all of that to be green hydrogen and produced sustainably using renewable electricity. So with recent government forecasts, in order to make all of this hydrogen at scale, at the terawatt scale sustainably, we need to hit certain efficiency and cost targets for water electrolysis. So particularly government guidelines have suggested that the efficiency of proton exchange membrane water electrolyzers needs to be increased from 72% today, going up to 82% by 2050, while also of hydrogen production by 50 times. So we need to reduce green hydrogen costs from about 120 pounds per megawatt hour going down to 70 pounds per megawatt hour. And this really boils down to us being able to find more active catalysts and more cheaper catalysts that can be able to catalyze hydrogen production by splitting water. So specifically, Anna also touched upon this, that current water electrolyzers have really high iridium loading at the anode, and iridium specifically is quite rare in the Earth's crust, and it's also really expensive metal for or metal oxide for catalyzing this reaction. So if we really need to scale up water electrolysis to the terawatt scale, we need to reduce the iridium loading by about 25 to 50 times to make this technology more feasible. So my research really involves trying to understand how different catalysts catalyze water oxidation or water splitting at the atomic level to then be able to design a more active and more stable catalyst for these reactions. So I'll be happy to take any more specific questions that you may have.
Okay, thank you, Reshma. So I'm delighted to see we've already got some questions. So please do keep on posting the questions. The more questions, the better. So maybe the first question I'd like to direct to Jason. So are biofuels really sustainable? How do we solve issues around land and water use, competition of food crops, etc.?
Yeah, I mean, it really depends, is the answer. So if you cut down rainforest in order to plant sugarcane, in order to make first generation bioethanol, it's not very sustainable. I don't know how you would even argue that it is very sustainable. If you're using second generation biofuels, a lot of the carbon savings depends on exactly what you use for a feedstock. If you take forestry residues, so basically wood that's grown in the forest, which does not use fertilizer as an input, which is actually quite a significant carbon savings in its own right, you get roughly an 80% CO2 emission reduction versus petrol. First generation biofuels like sugarcane ethanol, it's about a 20% reduction relative to petrol. If you use agricultural residues, then it's somewhere between 87 and 95% reduction in CO2 emissions versus petrol. A lot of that's because the carbon savings from not having the straw or the bagasse or the corn stover rotting and emitting CO2 and methane in the field. If you integrate your bioethanol production with carbon capture, which is actually what's done, I don't know if anybody remembers the CO2 shortage that we had last year. That was in part due to a Haber-Bosch plant shutting down in Germany, and the rest of it was due to the domestic CO2 supply being cut off because Vivergo and Ensis were both offline while the renewable transport fuel objective was being argued in Parliament. So if you do CO2 capture on your fermentation, your ethanol fermentation, and you use agricultural residues, then you actually have carbon negative bioethanol. that can be produced. So it really, really does depend. The land use question is an outstanding one. And as I said, I'm not a big fan of cutting down rainforests to plant anything, much less energy crops. And so we have to stick to marginal land, forests, in other areas where we don't use the land for food production.
So I have my own question to you, Jason, actually, on that topic. So what was the potential of, because my general impression is that if you look at photosynthesis, it isn't actually that efficient in comparison to solar cells. So let's say, obviously I would see that the kind of biofuels have an important role to play, but do you think that to what extent can we meet our future energy needs from biofuels?
I mean, it's an outstanding question. I mean, some of it has to do with input costs, right? Depending on exactly what you believe for a figure, this is plus or minus 20%, but 180 billion tons of cellulose grew on this planet last year without our doing anything. So that just happens. We had nothing to do with it. That's a lot of carbon. That would run the entire energy, fuels, and materials industry all by itself. We have estimated that somewhere between 1 and 2 billion tons of that could be harvested with no impact. So there's no impact on land use. This is quite important. If you think about the scale of use, the petrochemical industry is about 400 million tons of material. We produce about 3 billion tons of agricultural residue. So that's straws and things. So it's an order of magnitude higher. So those sorts of things are extremely important in terms of how you, I guess, do your accounting. And so it's not necessarily a fixed answer. If we were to dedicate all of those residues to producing energy, we could do a 100% transport fuel replacement with bioenergy with no problem. If we want to divert that material to primary electricity production, then you have to cut into the transport fuel supply. I personally tend to think that, solar and wind, at least until we have fusion, solar and wind are very reasonable options for electricity supply, but trying to make hydrogen and fuels from electricity would require us to then add on, right? So we need it all to be renewable, and then we need to increase it again. And so if we wanted to turn over the gas grid, we wanted to turn over all hydrogen and materials production, and we wanted to produce all of our electricity from solar and wind, we would need, I forget what it is, it's something like 100 times the amount of solar and wind that we currently do, which is actually quite a crazy scale-up effort. Mm-hmm. Biomass, we don't have to do anything. We just have to utilize what's rotting out there right now. So it's a lot easier. And so I think in sort of the 30 to 50 to 60 year time frame, it's a very good transition material as we get these other technologies up and running. TRL9 is a lot more attractive to me than TRL1.
Yeah, I understand. I mean, I guess, yeah, I can totally see that what you mean in the kind of medium term is probably easier to implement, but although maybe the longer term potential is higher for some of the technology. But I guess there's no single solution. That's probably important.
Yeah, we're all buying time for fusion. I promise.
But so I have another question now. So we've heard a lot about hydrogen at this festival. How are we going to make enough hydrogen quickly enough to meet the needs of all the sectors that are relying on it to decarbonize? So I'll pass this question over to Reshma.
So that's a great question, and I think scaling up of hydrogen is really the talk of the day, and it really relies on us being able to increase the efficiency of catalysis as well as really reduce the precious metal content within the catalyst that we are currently using. So, for example, today we use between 1 to 3 milligrams of iridium per centimeter square of the catalyst, and that's way too high if you need to make electrolyzers that can produce kind of terawatt scale hydrogen. So we need to reduce that by about 40 to 50 times, and finding ways to be able to reduce that iridium content, I think, is really critical, while still being able to develop supports that don't corrode under these conditions. So we can imagine as we reduce the catalyst content, we expose more of the support within these electrolyzers to these really harsh conditions. So we need to have stable catalysts, more active catalysts, lesser iridium loading, and better supports for electrolyzers, I think, is probably going to be the way forward for this.
Thank you. Okay, so I have another question from Zach Amin, who's asking, and this is a question for Anna, so are sustainable energy solutions such as wind and solar really effective in producing green hydrogen at scale? Are we not considering the physical space limitations? This touches a little bit on what we were discussing with Jason before, so Anna, please go ahead.
Yes, the rate of green hydrogen production is definitely an issue. So in terms of the systems I work on, photoelectrochemical systems, they will not be able to produce hydrogen at a sufficient rate to meet, industrial requirements. They will probably be more for decentralized support. So you can now have a massive field of PV and have some electrolyzers in the corner to make hydrogen in larger quantities than you'd be able to in probably photoelectrochemical systems. But again, that will not meet all the requirements. But then what are then the options? I think this relates to some of the other questions that were asked. So you could power electrolyzers from the grid, but as Jason said, that requires the grid to be completely green. Otherwise, there's no point in producing the hydrogen, because even though you don't pollute the streets with your vehicles or with whatever else you're doing with the hydrogen, you're still at the moment burning fossil fuels in order to generate the electricity. So if you want the hydrogen to be completely green, the grid has to be fully decarbonized. So then that comes back to what are the options for making hydrogen in the most environmentally benign way from fossil fuels. So that involves steam methane reforming, or as I think it was mentioned, pyrolysis. So the problem in the UK, this is a UK specific point, is that if you want to make hydrogen in a sustainable way from methane using steam methane reforming, you have to do something with the CO2 emissions. And yes, there is a talk of blue hydrogen, but that very much requires for the infrastructure for harvesting the CO2, transporting it and pumping it into geological reservoirs to actually be available. And as far as I'm aware, in the UK, that is not actually the case. So, and in order to build a sufficiently large infrastructure to generate all the hydrogen that we need by steam methane reforming and pump all the CO2 emissions, the infrastructure has to actually be built, and that will take decades. So yes, the photoelectrochemical and water plus electrolysis solutions are not, won't really compete in terms of scale, but at the moment, they appear to be more viable solutions than the other, if that makes sense. So until blue hydrogen actually becomes available, we might as well get on to doing everything we can to support green hydrogen production in other ways. But yes, certainly the issue of space is a big one, and the production of PV panels is not without CO2 emissions. So we're not saying that hydrogen production from solar energy is completely benign, but it's definitely more benign than the present option. Does that answer the question, Ifan, or do you want to add something?
No, I think that answers the question. I guess it's I think the when you, even if you have blue hydrogen, so I mean combining steam reforming of fossil fuels with carbon capture, there's always going to be some leakage of CO2. And I think there's if you increase the infrastructure too much, I mean, there is a place for doing it in the short term, maybe. But I think if you increase it, spend too much, all of your investments on that, there'll be a temptation not to invest much into green hydrogen in the medium term as well.
Yes, I mean, and reliance on methane, whether it's for steam methane reforming or pyrolysis, it doesn't solve the energy security issue of requiring huge amounts of natural gas to be imported to support the hydrogen infrastructure. So yes, all the arguments are to continue developing our kinds of greener solutions to hydrogen production, but that's my opinion.
And this is why everybody loves Beck's hydrogen production so much, is because, as I mentioned earlier, that is actually carbon negative hydrogen. The problem is that technology has not been proven at scale, and it's going to require, I mentioned the medium term, that one's probably more long term, but it is very attractive in that sense.
So I have a question for Reshma. So increased use of hydrogen has led to a strong negative response from some, focusing on the low energy density by volume of hydrogen and the use of renewable electricity sources to produce hydrogen, which we already touched upon. Which sectors do you believe hydrogen should focus on, and what is being talked about that will never happen?
So I think in the short, medium term, heavy duty transport, I think is one sector where hydrogen can really help us to start decarbonizing the sector. I think we're already seeing things like hydrogen buses, and I think even moving to the shipping industry would be an attractive way forward. I think hydrogen can also be used as an important feedstock for certain chemical industries like methanol production or probably even ammonia steel making, which are currently emit quite a lot of CO2. So I think that would be something also within reach in the more medium term. One area that I'm not sure which will ever happen, but I'd be excited to see it happen, would be the aviation sector, where I'm not sure the role that hydrogen directly plays. I think Jason mentioned there's probably more scope for things like biofuels in that area. I'm not sure the extent to which hydrogen might be able to contribute in that sector, but maybe Jason can provide some more insight about perhaps biofuels being the way forward for aviation.
I mean, it's a great question. I mean, I think all of we talk about transport, we talk about aviation. They are two very different problems. The legislation and the regulation, I should say, not legislation. The regulation around aviation is extraordinarily difficult to change, and so the possibility of bringing in hydrogen-powered planes or electric planes, while the technology may be in place in the next 10 years, the likelihood that that's going to be deemed publicly acceptable is pretty low. And so I think sustainable aviation fuels are almost certainly going to be biofuels, at least in the short term, probably in the medium term, until sort of the battery and hydrogen technology becomes established enough that people will trust it.
Thank you. So I have a question for Anna now. Again, so a group at ETH Zurich have demonstrated the technical feasibility of an entire thermochemical process for converting sunlight and ambient air, so CO2 and moisture, into drop-in fuels. CO2 and water are extracted directly from ambient air and split using solar energy. This process yields syngas, a mixture of hydrogen and carbon monoxide, which is then processed into kerosene and methanol. So solar is being used as CSP, and therefore it's a thermochemical process without the need to convert sunlight into power. This seemed to be a possible route to low-cost drop-in fuels. This question was from Professor Brian Scott Quinn from ICMA in Reading.
Mm-hmm. So I better start by saying that I don't know the details of this technology, so my answer is a bit more, let's say, intuitive, but it does seem that harvesting CO2 from the atmosphere is essentially a really massive fight against entropy. So, for example, if I were to take a flight right now, calculate what my CO2 emissions are, and then work out how long it would take for this technology that you mentioned, and how much area it would take to actually convert my emissions back into something useful, I'm sure the answer is, not going to suggest that that's the only route that we're going to take to generate the fuels, just simply because it won't be possible at a sufficient rate and at sufficient scale. I don't have the numbers though, so please feel free to post an argument against that. But so I'm not saying that it's not a useful technology. It's certainly a contributing one, but I think we're all kind of having to accept the fact that we're going to need a portfolio of solutions, right? So just because one technology can contribute to kerosene production and methanol, that doesn't mean that other technologies that are best situated somewhere else geographically, whether it's because there's more wind there or more solar energy there, that they can't be seen as contributors. I think you just have to be sensible about what technology you pick for which location. So there's an argument that solar is possibly not the best solution for the UK, let's say, but maybe it's a very sensible way of making hydrogen somewhere like Spain or South Africa. But again, even that isn't stopping from so my field's very multidisciplinary, photoelectrochemical reactor design. It requires not just materials, electrochemical engineering, it requires specialists on optics. So there are people working on ways of harnessing and concentrating diffuse light in waveguides and other very interesting photonics. So a lot of effort is happening to try and really maximize the use of natural resources to their fullest extent to support the production of various fuels, and I don't see why that's a problem.
I do know the details of that, and I can confirm that Anna is exactly correct. The technology is very interesting, the approach is very exciting, but it is extraordinarily slow. So the question had one inaccuracy in it, which was low cost. Kerosene is low value, but that production method is not going to be low cost. I had run the numbers thinking that a refinery scale plant using that technology would be roughly the size of Texas, which is one of the biggest US states. Turns out it would be slightly larger than planet Earth. So no, it's too slow at the moment. So it's exciting, but refineries don't run on the hour scale. They run on the millisecond time scale. And so that production, the entropy that Anna mentioned of getting the CO2 out is at the moment insurmountable.
Okay, thank you. So there's another question. I'll answer this question. Everything is based around combustion of carbon with oxygen. Are there any other reactant combinations that could be developed? That's true right now. Carbon with oxygen is pretty important. I think that as I was mentioning earlier, there are another alternative which would be to make hydrogen from splitting water, which Anna and Reshma have talked about. And then when you burn hydrogen, so there's another question asking if you make any emissions, when you harmful emissions when you burn hydrogen, and the fact is that actually you only make water. So if you get hydrogen from either from by directly splitting water using sunlight, or by making renewable electricity, and then splitting water into hydrogen and oxygen, in principle you have negligible emissions. So so hydrogen obviously is a combination with oxygen that won't make any CO2. Another option would be to use ammonia as a fuel, and it's particularly interesting for shipping. And it's liquid, it's got a high energy density, and it doesn't contain any carbon. And if you burn it correctly, then you just make you just get nitrogen coming out of it and water. So in principle, it could also be emission free. Has its disadvantages. It's toxic, so you have to make sure that it doesn't. So there is debate about whether hydrogen, for example, ammonia, would be better as a shipping fuel. But so it does have its disadvantages, but it also has a lot of advantages. So for the next question. So this is a question for Jason. What are the most significant factors contributing to cost and emission during biofuel production?
It really does depend on which biofuel. So I'll stick with bioethanol because that's sort of the easiest one to handle. But there are alternative fuels. There are alternative production technologies. But I'm gonna stick to sort of the biochemical right to bioethanol because that's considered to be the most benign. The biggest cost problem in second generation bioethanol is actually the crop harvesting. So it's actually the input, the biomass input. So first generation bioethanol, that is direct sugars. So that's food crops, starch, corn, wheat, that sort of thing. Those are the only bioethanol plants that are operating in the UK or first generation. Second generation biofuels, which are the ones that are much more sustainable. The biggest issue is the recovery of the sugars from the biomass in the first place. So a tree is somewhere between 70 and 75% sugar, but you wouldn't know it. So trying to access those sugars can be extraordinarily expensive. That happens to be what I work on as a research topic, so I'm of course very much a proponent of it. But that is a huge cost driver, and it's actually overshadows the cost of the feedstock input. You can use a lower cost feedstock, which is helpful, but you have to do more extensive processing, which costs a lot more money. As far as emissions, they come in two sources. Number one is the processing itself, so what I just mentioned. So the conversion technologies require, of course, heat and some sort of either chemical or electrical input in order to run the process. And secondly, of course, when you ferment sugar to make ethanol, you get 51% of the carbon turning into ethanol and 49% of the carbon turning into carbon dioxide. At the moment, in the UK, we capture 100% of that carbon dioxide and use it basically to make beer, or I'm sorry, beverages. I'm sure some of it goes to soda, but actually it's pretty much all beer. And so that's where all of our food grade CO2 comes from in the UK, is from those two bioethanol plants that I mentioned. If you were to go to massive scale and produce all of the world's fuel supply with ethanol, we would need to figure out a way to transport and store that carbon, as Anna alluded to before. And so that becomes a significant emissions reduction concern. So, you know, if you do nothing, then only half of your carbon is being transported into fuel and the other half is just being emitted directly. The nice thing about biofuels is that no matter what you do, all of the carbon came out of the atmosphere. And so the worst you can do is neutral emissions.
Okay, thank you, Jason. So I see a question that I'd like to answer actually. So what role do you see for low and high temperature electrolysis of CO2 and nitrogen to produce carbon-based fuels and ammonia directly using renewable electricity? So I think the answer to that, first response to the question about CO2. So right now CO2 is, you can actually get CO2 reducing electrolyzers. So the Danish company Haldor Topsoe, they make they use a high temperature electrolyzer cells operating, I believe, around 1,000 degrees Celsius, maybe slightly higher, slightly lower, and they reduce CO2 to CO. So the main motivation for this is not to use it as a fuel, but rather because carbon monoxide is something that's very it's flammable and it's toxic and it's a pain to transport. So CO2 is easier to transport, and so a lot of companies prefer to have an electrolyzer. So you don't have to deal with an excess amount of CO. You just make them exactly the amount of CO that you want. So and CO is a really useful reactant, for example, in the pharmaceutical industry. However, so of course, so I think that there is a lot of interest in actually doing CO2 reduction to actually making sustainable fuels as well. And right now, you can't buy an electrolyzer that does this commercially, mainly because if you want to go for the really energy-rich products, for example, ethanol or methanol, the direct electrolysis isn't quite efficient enough. But there has been a lot of progress in the field, especially in the last 5 years in this area, in direct electrochemical reduction of CO2. Especially at low temperatures, you can make carbon-rich products with multiple carbon bonds, especially ethanol and ethylene, but just not a high enough efficiency. But I do think that if you look at the progress both in materials and engineering, it is advancing quite fast. So I think there is a case to be made for making sustainable fuels in this way. I think one thing that's quite interesting is that usually it's much more difficult for companies to enter the energy market than to make kind of fine chemicals, for example, using electrochemistry, because like I said, for the example with CO2 reduction to CO, then there's a lot of logistical and safety reasons which make it more attractive to make CO using electrolysis. However, there's huge incumbents from fossil fuels if you want to make fuels, and fuels are generally lower value than a lot of the chemicals like carbon monoxide. But obviously, if you want to, a chemical like carbon monoxide is not good as a fuel because it doesn't have a lot of energy in it. For nitrogen reduction to make ammonia using renewable electricity right now, nothing really works very well. There's some things work at very low efficiency. This is something that I'm researching in my own lab, but we're still quite far off from actually using making electrolytic ammonia, but it is again a fast-moving area, and there's been a lot of progress, especially in the past 2 years. So really watch this space, I would say. But it's not. But we're not there yet. We're very, very low technology readiness levels. Now reading on with the other questions. So actually, I want to go up and ask a question for Anna. So what is the status of artificial photosynthesis? Is it a feasible, sustainable energy source for the future?
Well, so my work involves trying to make it a contributing technology, but the status is that most of the work is still being done on materials. So that's currently still the bottleneck. So I'm pretty sure that if I invite the audience to imagine PVs coupled to electrolyzers, you can picture it, right? A field of photovoltaics, some electrolyzers in the corner, producing hydrogen. But if I would say picture a photoelectrochemical reactor, I'm pretty sure that no one would have kind of any mental image of what that might look like. And that would be because there aren't actually many prototypes out there. So there are some upscaled lab demonstration units, not all of which have been successful. And in Japan, there's a slightly different technology for using photocatalyst sheets that's being upscaled. But apart from that, there's very little, very limited development. And part of the problem is that there aren't actually enough electrochemical engineers or even photoelectrochemical engineers working on these developments. But that's where I come in, for example. So my background is in electrochemical engineering and also in physics. So I'm combining all of these disciplines to the design of photoelectrochemical systems, because I think unless we come up with some actual prototypes that show that they can produce some sort of non-negligible, respectable amount of hydrogen, then the technology won't really move forward. So my ambition is to move it forward. And I guess encourage also more material scientists to think about routes to scale up the materials that they're working on.
So I have another question now for Jason. Thank you, by the way, Anna. So can algae be used to make fuel and oil from sunlight and water?
I mean, yes and no. Algae do, in fact, make oil from sunlight and water. That is literally what they do. The issue with trying to make fuel from algae actually is the water. So this is a huge issue. Algae grow at a density of roughly 1/1000th in water. So if you have a pool of algae, it's 99.9% water and 0.1% algae. So the carbon yield is enormously low per unit volume of water. And that technology has proven unscalable because of that issue. The other big issue is, of course, the dewatering, the expensive dewatering downstream. So removing the water from the algae during the processing negates a lot of the, I guess you could say, carbon emission savings that you got from capturing the sunlight directly. So it's a real challenge. We need to figure out a way to grow algae without using water. If we could do that, then I think it would be an extremely viable technology. Algae are very stubborn little bastards. They would much rather produce algae than produce lipids, so biodiesel. They would much rather produce offspring. And this is also a big issue. Convincing them to make fuel rather than protein is very hard. The more comfortable you make them, the more sunlight you give them, the less fuel they produce. And so you have to sort of keep them at the right level in order to make that happen. So it's a scalability concern more than anything else.
So, okay, thank you. So I have another comment saying, by far the cheapest and most effective way of cancelling both direct CO2 and indirect CO2 effects from burning aviation fuel is to use direct air capture. At $100 per ton CO2, low-cost oil producers such as Saudi can produce net zero, net negative kerosene at much lower cost than any alternative. Though economics will drive this, and it doesn't apply to aviation. Any transport heat fuel can and should be offset on the one in 1-out emission basis. There's no new tech involved, as we already have direct air capture available at high TRLs. There's no significant thermodynamic issues in limiting air capture of CO2. Does anyone want to comment on that?
I'm not sure I quite understand the part about no significant thermodynamic issues with the air capture, direct air capture of CO2. That is flies in the face of not only conventional wisdom but thermodynamics. So yeah, I'm not quite sure I understand that part. The estimates I have seen at the moment for the high TRL direct air capture technologies, or at least the large scale direct air capture technologies, run between $300 and $1,000 per ton of CO2. It is unlikely that we would ever get a carbon tax. I'm hoping for $100 a ton. Hoping, it probably should be about $200 a ton, to be honest. I actually think at $200 a ton, all of these problems would be solved. But most people seem to think it's going to be more like $50 a ton. And I don't think direct air capture is well, the estimates I've seen, the economic estimates I've seen, direct air capture suggest that there's a lower limit of about $80 a ton. That anything lower than that's pretty much impossible. And so it would have to be done indirectly at that point. I'm a big fan of indirect air capture because growing plants is an outstanding way of doing indirect air capture. So it really depends what you do with the carbon management downstream. But no, I'm not quite sure I agree with the assertions in that question.
No, I think I agree with you that it doesn't seem like it's that cheap right now. It would be great if we could use more direct air capture, especially I think some things it's going to be difficult to go to net zero if you really don't have some way of, because as you said, some things are always going to make CO2.
It is impossible to get to net zero without direct air capture, and to be honest, it is probably at this point impossible to comply with the Paris Accords without having direct air capture at some point. I mean we've probably already passed the point where direct air capture deployment is going to be inevitable. I have to say it's very silly. We put that CO2 in the atmosphere in the first place, and now we're going to go to all this trouble and expense to take it out again. But that just shows you how stubborn we are about decarbonizing in the first place.
Okay, so I think we should probably close off soon. So I have one last question. Maybe I'll direct to Reshma. Slightly off topic. But how optimistic is the panel that we can meet the Paris climate targets? What gives you hope?
So I'd like to be optimistic. I wouldn't like to end this saying we're not optimistic about meeting the Paris targets. But I think in a lot of ways we're talking on quite positive terms. We're going in the right directions with all the technologies and with governments at least acknowledging that we have issues in terms of climate change, but I think the speed at which we are going is probably a bit too slow. So while we have the correct direction, I think we need to be quite more aggressive in terms of, like what Jason was saying, in terms of having these carbon taxes, in terms of speeding up the technologies that we can develop. So I think there's still room to significantly improve what governments and companies, industries, as well as academics are doing. But I think it's quite positive in terms of the spirit in which things are moving.
I would agree with Reshma. I think that there's, I guess if we've touched on the three different ways, I guess, you can actually decrease emissions. So there's government policy, for example, carbon tax, as Jason highlighted and Reshma mentioned, and then you can optimize current technologies through better engineering, for example, and then there's obviously the kind of disruptive technologies, which could be really big game changers, which require, I guess, strong fundamental science. And these are the things that obviously, since they're disruptive, we can't predict them right now, but we have some ideas where we might be able to get them. And I guess the last part was what gives us hope. I guess I think it's really exciting to in the kind of I've been working in this kind of renewable energy for now almost 2 decades, but I think there's been a huge change in the discourse. So I think even like 10 years ago, people were scared of actually even mentioning climate change. They were just talking about energy security. That, especially after the COP in Paris, I think that that changed. also the US government's policy has changed, British government policy, EU, that acknowledging climate change is an issue. But I think like what Reshma was saying, we really need to go from ramp up the gear, to go into turbo on our efforts, and not just talk about it and really have action. Okay, so I think to give you a break before the next talk, I think we should wrap up. So I'd like to thank the speakers for not the speaker, the panel for excellent inputs, and also the audience for all these fascinating questions. So I should mention that the Future Energy Festival continues shortly with a series of lunchtime lightning talks and demonstration of a variety of energy-related topics, including redox flow battery, structural power composites, and Britain's energy under lockdown. Follow the link in the question and answer to join the next session. And after lunch, we'll have another panel discussion, this time on a really important issue, which is how to improve equality, diversity, and inclusion in the energy sector. So right now there are too many barriers, I would say, for having a diverse energy sector, and this is actually impeding the rate at which we can actually get to net zero. So guests include Energy UK CEO Emma Pinchbeck, Powerful Women's Rubina Singh, National Grid's Rodney Williams, and Professor Mustafa Özbilgin from Brunel University. So that starts at 2 p.m. and the link is also in the chat. So you can find out full details of all the Future Energy Festival events on the Energy Futures website. The details are on the screen. So I'd like to thank you all, both the panel members and the audience, for this really fun discussion. Thank you. Bye.